it looks good to me. So
yeah. I think it's okay. If you're worried about whether people can see, if you are worried you can see the chat from people, I think we can help you. If there's
you can see me. I can't see myself, but you can see me.
Your video is off, I think.
Press the escape button and then it removes from full screen to the corner of the screen.
Okay, let's see. I think I can. All right.
Press the escape button on the keyboard, not on the screen.
I should do what?
Press the escape button on your keyboard, the very upper left button, escape, ESC. Then it goes from full screen to part of the screen.
On Keynote.
Not with your cursor, with your finger on the keyboard. You're moving your cursor, and you should move your finger to the keyboard and the upper left key.
Yeah, I did escape. Yeah.
And then it'll go to the corner of the screen instead of full screen. Then you can toggle it back and forth by pressing that button with your finger.
Okay. I think I'm okay. Fine.
Okay.
You can.
Sorry. I won't interrupt. I'm just listening.
Chandra, by the way, I think your video is off. Do you intend?
What is off? What is off?
Your video, so we cannot see you. So is this intended?
You can hear me, but you can't see me.
Yes.
Now you can see me?
No, I cannot see you.
That's very strange.
Yeah.
Will I start again? Start from beginning again?
I think your camera may be off.
I don't know how that happened.
Have a look on this the panels. There should be some a list of selection things from Zoom that you can choose. Did you see this?
Well, you have to hit the escape button first, Chandra. Otherwise, you won't see the Zoom panel.
Yeah, I am on a.
You have to hit the escape button before anything on the keyboard.
Yes, I did.
Have you got that?
Okay. You can hear me, but you can't see me. Is that it? Can you hear?
Yes, we can hear you, but cannot see you.
The first step is for you to hit the escape button on your keyboard.
I don't know what happened here.
Not with the mouse, with your finger on the keyboard.
Okay, my video is on.
Okay, so.
You see my screen?
Yes, I can see your screen. Yeah.
Okay.
I think it's fine. Yeah.
Okay, let's start.
Yeah. Okay. So, Jimmy, shall we start now?
Yeah.
Yes, please.
Yeah. Hello everyone. So we will start now. So today it's our great honor to have Professor Chandra Varma as our speaker for the seminar series of high-Tc superconductor. So Chandra is now an Emeritus distinguished professor in University of California, Riverside. He is also a visiting professor in UC Berkeley. Chandra has made significant contributions to high-Tc superconductor, including the proposal of marginal Fermi liquid and loop current order. So today he will talk about loop current order and quantum criticality in Cuprates. So let's welcome Chandra. Chandra, you can start now.
Thank you very much. Incidentally, my title for bureaucratic purposes at University of California, Berkeley is recalled professor. I don't know what that means. Many thanks to the organizers for arranging the series of seminars and giving me a chance to present aspects of my solution to this problem, the problems in the cuprates. You have more or less seen this phase diagram. Do you see my cursor, incidentally?
Yes.
Okay. I cannot see it. let me try to see if I can do something about that. Or let's just continue. Okay, so you have seen this phase diagram more or less in every talk on this series. And rather than give details of the solution or attempts at solution in each of these regions, I'm going to present you with a general overview on the motivation and my approach to the problem, which has been somewhat different from the most popular manner of approaching this problem. My talk is organized along these four following lines, which is more or less the manner in which I have, or the historical way in which over these past 30 years, I have tried to look at this problem, first trying to understand the strained metal phase, waiting for experimental confirmations of the ideas of the marginal Fermi liquid, and then going on to the what the broken symmetry of the pseudo gap phase may be, which was implied by the quantum criticality in the first part, and then to go and try to calculate the fluctuations of the loop current order to get the omega over T scaling, which was the hallmark of my idea proposed with Elihu Abrahams and Schmetterling and Ruckenstein and Littlewood, and then do a detailed quantitative comparison of predictions for strained metals and superconductivity, including trying to decipher on Xinjiang Zhao's experiments in IOP Beijing as to the fluctuations causing superconductivity. I will probably get to this part on superconductivity only if I have time. And then finally, something which I found the hardest to do, doing topological decorations on the loop current order for Fermi arcs and magneto oscillations. This part is rather new, and I would say that this part is not completely verified in experiments. There are some experimental predictions, although there's just been one experiment now which I will talk about. So this, as I said, is the schematic universal phase diagram of ITC cuprates, and I put in my talk, in my slides, some references which you can look at if you wish to follow my way of thinking in detail. As I said, my way of thinking on this problem has been somewhat different from the most popular, and it could be summarized in saying that right in the beginning of at the beginning of the discovery of ITC, soon after, there was a great theoretical schism that developed, which was a question of what is the central problem to understand. I should use the word great here in quotes because on one side was almost everybody, and on the other side were my collaborators and me, my immediate collaborators and me. So one way of thinking about the problem is that the fundamental issue to understand is the passage from the half-filled case to the right as we dope. I'll concentrate on just the whole doping. And from that point of view, there was the idea that the minimum necessary model is the Hubbard model, and then within weeks after the discovery of ITC, Anderson proposed that is the model, and that led to the idea of RVB on one side, and also that the minimum Hubbard model is, if it is not RVB at half filling, it is an antiferromagnet, and then the idea that the central issue was antiferromagnetic fluctuations. I'd already worked on antiferromagnetic fluctuations for D-wave superconductivity by proposing with a bunch of people that they promote antiferromagnetic fluctuations, promote D-wave superconductivity. And I think I understood it well enough to say that this is not the central issue in the cuprates. With regards to RVB, it's a lovely idea. However, I felt that the moment antiferromagnetism was discovered at half filling rather than RVB in the cuprates, that should have been abandoned. That did not happen. However, I believe that RVBs or cousins of RVB is a very, very important problem in two-dimensional magnetic insulators at half filling, giving rise to spin liquids. But my current feeling is that spin liquids are much more exotic and interesting than what the ideas of RVB suggest for them. My idea, on the other hand, was that the central problem was to understand the normal state near half filling, which was very soon realized is not a Fermi liquid, and from that followed a particular idea of the quantum critical fluctuations, and the feeling was that a more general model is necessary, which should have unusual ordered phases, which would not be there in the Hubbard model, and from the unusual ordered phases derive the quantum critical fluctuations. And this is the point of view that, as I said, I'm going to follow. Now, in looking at this phase diagram, or in reading this phase diagram and the properties in various parts of it, one should be cognizant of the relative thermodynamic importance of different transitions or crossovers or of the different phases. And let me just state that if we normalize the free energy reduction by the maximum superconducting condensation energy, then the antiferromagnet phase close to half filling is about 10 times bigger, 10 to 50 times bigger. The pseudogap phase is near the critical point or about the critical point, about as important thermodynamically as the superconducting phase, but it grows in magnitude as you move further to the left of the periodic, further to the left of this phase diagram, to be almost as important as the antiferromagnet. And then there's a crossover to the Fermi liquid. There are lots of other things which are marked by dotted lines, the charge density waves, a low temperature spin glass phase quite often found, and many other things that happen. But thermodynamically, they are between 10 times to 100 times smaller in importance to the superconducting condensation energy. And I believe that that we should, they are not the principal problem, they are sidelights, and one should ignore them. I've also had the strong feeling, and it's only a feeling, that this is really, apart from the antiferromagnet, which is a signature of strong correlations, which are important everywhere, essentially everywhere in the phase diagram, that there has to be one central idea from which the strange metal phase, the pseudogap phase, and superconductivity should all follow, and they should be derivable systematically. Obviously, exact solutions are not possible, and they should have clear and verifiable predictions. So let's go to the strange metal phase. So within a year of the discovery of superconductivity, it was realized that in all the cuprates, and there were, by that time, there were 6 or 8 families of cuprates. It was realized that—
Can I interrupt?
Sure.
Do you feel then that the cuprates are entirely different in mechanism compared with the iron-based superconductors?
The immediate answer is yes. If you see here, I mentioned that there is a this antiferromagnetic quantum critical point that I point out even in the cuprates. If you look at experiments above the spin glass phase, that has very much the same properties as about the quantum critical point, about the superconductivity in cuprates. So I believe that that there is a certain universality in the cuprates about the antiferromagnetic critical point and this critical point, and that the problem in heavy fermions and in the iron-based compound is a problem of properly understanding the nature of the antiferromagnetic quantum critical fluctuations. I will speak more about that at the end, but unquestionably in heavy fermions, as you, if it's Doug, you and I suggested, the D-wave superconductivity is due to antiferromagnetic fluctuations. In cuprates, it is not. However, at some universal level of quantum critical fluctuations, there has to be a similarity because the properties in the strange metal phase that I'm going to be describing are the same in the heavy fermions and the iron-doped compounds, although not so clearly exhibited experimentally as the properties I'm going to be talking about in the cuprate. So to go back, there was clear evidence that Landau's idea of quasi-particles is not valid in this central region, and it was manifest in essentially every property that one studied, and it was important to look at each one of them and to see if something could be said which was central, from which everything else followed. And from that idea grew the idea of the marginal Fermi liquid. So here I've divided my screen up to the central issues in a Landau Fermi liquid. In a Landau Fermi liquid, due to Pauli principle, we know that if we look at the response of any property, be it magnetic fluctuations, spin fluctations, current fluctuations, or generically density fluctuations, that at omega small compared to the momentum transfer times the Fermi velocity, they're linear, omega over kVf, and then there's a cutoff due to phase space restriction at 2 times kVf. So there's a low density of low energy excitations, which leads to scattering rate of electrons proportional to T square, and that makes the quasi-particle picture due to Landau work. It's amusing to realize that this spectrum, if you go into Fourier transform it into imaginary time, it goes as 1 over tau square times the signum of tau. This was not working, so my colleagues and I proposed that the central point was that there had to be response functions in which at low energy, the fluctuations are scale invariant. They go as omega over the temperature of measurement, and then for omega much larger than temperature, they are nearly a constant up to some cutoff in the problem given by the microscopics of the problem. You see that as temperature goes to 0, this becomes, because imaginary part of response functions or retarded response functions have to be odd in frequency, this becomes discontinuous, and if you take its real part, it has a log omega singularity. So we were positing a criticality, and another way of saying that is that the fluctuation spectrum in imaginary time is 1 over the imaginary time rather than 1 over tau square as in a Fermi liquid. Now, if you have high density of low energy excitation controlled only by the temperature of measurement, it's very easy to show that the scattering rate of electrons is proportional to temperature if temperature is much larger than frequency, or proportional to omega if omega is much larger than temperature. Another very crucial assumption that we had to make, and that was a horrifying assumption to make, that this fluctuation spectrum is more or less independent of momentum. There are no singularities as a function of momentum. And in the microscopic theory that I will derive, whose answers I will relate, this horrifying assumption is gotten rid of, but all other properties remain. Now, the important part about this, as in for any theory of cuprates, is that it predicted certain experimental properties. For example, the combination of scattering rate proportional to T on omega and independence of momentum predicted that, stated that the resistivity is linear in T. It gives the NMR relaxation rate, the Raman scattering, the optical conductivity. It also predicts that the specific heat goes as T log T because the real part of the self energy goes as omega log omega. Now, I would say at this point that this spectra that is postulated is necessary and sufficient for the quantum critical properties in the cuprates, and I believe it is quite possibly unique. I'm more and more inclined to the point of view that it is unique, and therefore the same fluctuation spectra should occur for different completely different microscopic reasons for the heavy fermions and for the iron compounds. It also has to be realized that this cannot be obtained in conventional quantum critical theories, the Hertz, the Moria, Millis kind, which are extensions of dynamical critical phenomena, classical dynamical critical phenomena to simply to quantum fluctuations. So given the phenomenological success of this, this assumption of omega over T scaling, one had to answer the following question. What are these fluctuations made of? We had no idea. We had to derive them for relevant models in a systematic manner. And there's a very important question, which I will return at the end of the talk. How can superconductivity, due to the same fluctuations that are, whose scattering, single particle scattering is angle independent, how can, which is experimentally known now, produce your D-wave superconductivity when Miyake and Schmitterink and I had proposed D-wave superconductivity from anti-ferromagnetic fluctuations in heavy fermion, the scattering rate was strongly angle dependent. And then finally, compare with experiments. So now I come to the second part of my talk, which has to do with the pseudogap phase and loop current order. So the proposed spectra was quantum critical. And after fiddling around for a couple of years, trying to make various models with those properties, which had quantum criticality over the whole phase hag, over over the large region of momentum space, of doping space, and failing, there was a realization that this can only happen if there is a line of phase transitions ending at a quantum critical point. And by that time, there were experiments that had come about which showed that on the line that I showed here, the T-star line, thermodynamic and transport properties change in a colossal fashion. As I said, from the change of entropy or change of specific heat from T-star to below T-star, you can estimate the characteristic energy reduction in the pseudogap phase, and it's substantially larger over most of the range than due to superconductivity. The problem was that there is no signature in the specific heat of a singularity at T star. However, I still propose that T star is a line of phase transition, that some symmetries must break, and I suggested a specific symmetry change, but first one had to talk of what model would have this phase. As I said, it cannot be the one orbital per unit cell Hubbard model. Now, to think of a model, one has to know some chemistry, and I was fortunate enough in the late 1970s, early 1980s, to work on a chemistry problem. And the chemistry problem was, what is the chemisorption energy of simple gases across the transition metal series? And you found that the chemisorption energy of, say, nitrogen was essentially zero on copper or nickel, and was substantial on titanium and vanadium. And also, if you put O2 molecules on the transition metal surfaces, then from scandium to nickel, they dissociated, but on copper and zinc, they stayed as molecules. And in understanding this, I learned that an obvious fact, that the center of gravity of d bands, or the position or the affinity energy of transition metals, systematically decreases from the left to the right, and the ionization of energy, which is marked here by a hard line, crosses the affinity energy at near copper. And this was also enshrined in the so-called Zanen-Sawatsky-Allen diagram, although in the beginning I was not aware of this. What this meant was that the excitations in copper oxides were a single particle excitation for jointly on copper and oxygen. And quite possibly what was unique about copper oxides was that the Hamiltonian had to be thought of in the space of 3 orbitals per unit cell, not dpx-py, with kinetic energy between coppers and oxygen, between the oxygens, local repulsions on coppers and oxygens, and very importantly, ionic interactions between copper and oxygen, because after all, there were charge fluctuations between coppers and oxygen. Because of the ionization energy and affinity being similar of copper and oxygen, this model cannot be reduced to the Hubbard model. In fact, people who tried to reduce it to a one-band model made the assumption that the difference of copper and oxygen energies is much larger than the transfer integral, which I did not believe is true. Although in none of these models you can know the specific numbers accurately to within factors of 2, because all the numbers that appear are effective numbers and not easily calculable. Now, given this model, I asked myself what new phases could arise which were by the mid-1990s not already ruled out by experiment. And I felt strongly that broken translational symmetry was not what was happening at T star. So I had to think of something else, and also that there was no kind of spin order appearing at T star, things which are now completely verified. So, and also there were by that time 100,000 experiments. So what could you predict which had to be very hard to detect and which could not have already been detected? Now, there are various ways of expressing this loop current order and its motivation. Probably the simplest is the strong coupling limit. Supposing you take those U parameters, very large compared to the kinetic energies, and take the V parameter, the copper-oxygen interaction energy, also large compared to the kinetic energy, then just as you derive the Heisenberg model from the Hubbard model, from the three-band model, you can derive an effective model for interaction, which has a parameter J times, it's like a Heisenberg model in spin space, times an anisotropic pseudo-spin interaction model in orbital space. What do I mean by orbital space? So let's consider the orbitals, the three orbitals in copper and 2 oxygens per unit cell. You can make an antibonding orbital, which is D plus Px plus Py. You can make a bonding orbital, which is way below in energy, and I can neglect it for the moment. The nearest other orbital is a non-bonding orbital, Px minus Py, which you see obviously is orthogonal to this other orbital, which is a linear combination of Ds and Ps. And if any expectation value of this, so this tau is defined in the space of these two orbitals. So if any of the taus has an expectation value, something else happens. Well, to cut a long story short, if tau2 is non-zero, if the expectation value of tau2 is non-zero, that amounts to saying that there is a vector potential on the links between copper and oxygen, or a phase shift coming in the transfer integral between coppers and oxygen. And then if that happens, the effective Wannier orbital is complex. If you add these two with a imaginary coefficient, you get D plus 1 plus I theta Px plus 1 minus I theta Py, which is saying that on the triangle, there is a 2 theta flux. And theta is our variation parameter, which makes your tau2 non-zero. And the next task was how to organize these triangles. And it turns out really that there are 3 distinct ways of organizing these triangles. I went for the simplest first, which was wrong, and in 1999 proposed this order parameter, where in each unit cell there are 2 copper oxygen loops going in clockwise and anti-clockwise direction. This is called a toroidal moment or anapole order parameter, which is this quantity omega denoted by this big arrow in the middle, which is the integral of the magnetization at a point crossed with its location. So from here to here, it goes in this direction, and here the moment is opposite, and this is the R vector, so again, it goes in the opposite direction. Now, this order parameter preserves translational symmetry. It breaks time reversal, it breaks fourfold reversion, it breaks inversion, and there are 4 possible orientations of this vector omega. Now, this is a bloody hard order parameter to detect in a magnetic diffraction experiment, because it will produce you Bragg spots, which are magnetic Bragg spots, which are right on the top of existing nuclear Bragg spots. But there are lots of other experimental consequences because of breaking time reversal and inversion. Now, the most detailed calculations on this model is a variational calculation done by Christian Weber in his thesis with Thierry Giamacci. They took this model that I have described to you with EP minus ED, which is this delta now the local repulsion on copper and oxygen, and did a gigantic variational Monte Carlo calculation. And the calculation the variational calculation consists of putting in a phase shift in the kinetic energy of the orbitals, arbitrary of symmetries, and putting in an effective distance in energy between copper and oxygen, even a magnetic field, and then interactions, and varying this thetas in all possible ways, and deltas and h's. And what was interesting about this variational calculation was that there was a benchmark put by exact diagonalization on a 24 site or 8 copper oxygen unit cell, okay, or you cell, 24 sites. And when you calculate the phase diagram and vary parameters, you found this phase diagram on the space of the distance between copper and oxygen, this EP minus ED, and hole doping. Near half filling for EP minus ED larger than about 1, it is a spin density wave. And if EP minus ED is large, you simply go from spin density wave to a D wave superconductivity to a Fermi liquid. However, for EP minus ED less than 1.5 eV and above some value, you go from the antiferromagnetic phase to the loop current order of the symmetry that I described to D wave superconductivity to Fermi liquid. And this is really the most elaborate numerical calculation that I know of, and a lot more can be done by people who are proficient in doing such things. I certainly am not. However, the most important thing are not the calculations, but to see whether the different symmetries that are predicted are indeed experimentally observed. And as I said, these are hard experiments, but over the years, there is a whole variety of experiments looking for time reversal breaking, inversion breaking, four-fold symmetry breaking, and various other properties which were in fact experimentally predicted. The most detailed experiments are polarized neutron scattering. And I'm not going to describe each of these experiments, but simply say that in one compound, yttrium, barium, copper oxide, polarized neutron scattering saw this phase occurring below the green square shown in this diagram, with the transition temperature systematically decreasing and finally not being there above some 20% doping. This experiment has been done in 4 different families of cuprates, always detecting the same symmetry. There was an earlier experiment of which I had proposed to look for this phase of dichroic, angle resolved photoemission, and BISCO. There is carrier effect in BISCO occurring identically to this line, and there's a lot that can be said about it. There is second harmonic generation done by Liao and David Shea, also indicated by the brown circular lines on yttrium, barium, copper oxide. And I'm going to not dwell on these things except a bit on neutron scattering. But I should say that while these experiments are generically consistent when they measure symmetry with the specific phase that was suggested, there's a new experiment which should be online on arXiv in a week or so by Sejun Lim and Aaron Kapitelnik. And as I will talk about this, it's a very sensitive experiment and a very detailed experiment the photogalvanic effect, and it finds experimentally a different symmetry. And the way the different symmetry is found is very interesting, and I'll dwell on it. But let me just show you how detailed the neutron scattering experiments are. So this is Philippe Bouge and collaborators. And on the left, I show you the yttrium barium copper oxide experiments at the magnetic scattering at different dopings with 6.5 on the top and the oxygen 7 at the bottom. And there is and this is done with polarization analysis, so you know that it is magnetic scattering, and you discover that the transition temperature is systematically decreasing as you increase the doping. What I show on the right is really quite extraordinary. In blue is shown a Bragg peak whose intensity is shown on the left. And on the right, at the Bragg's peak expected for that particular structure, the magnetic intensity is shown, and you see that it essentially overlaps the Bragg peak. From quantitative measurements, one can say that the measured magnetic moment is 1/10 of a Bohr magneton per unit cell. And let me just remind you that if you had Ising order of 1/10 of a Bohr magneton per unit cell at 100 Kelvin, that will have a free energy reduction, which is similar to the maximum measured superconducting condensation energy in Cuprates. And the number, if instead of Ising model, it's some other model, XY or Heisenberg or whatnot, those numbers change by only factors of 2 or thereabouts. Here is a experiment on neutron scattering done in Graven's group together with Philippe Bouge on mercury cuprates. And again, 3 different dopings are shown. The bottom here does not show any extra magnetic peak. You see, in black is being shown the non-spin flip or purely Bragg scattering, and on the colors, green, red, and blue at different dopings, the magnetic scattering. And magnetic scattering is tiny compared to the nuclear Bragg scattering. That's why it's hard to discover. Very interestingly, if you take this sample B and you anneal it and reduce thereby oxygen, reducing Tc from 83 to 61 K, we know that the zero gap transition temperature goes up, and you can see that the effect here on the right occurs at a higher temperature and has a higher absolute magnitude compared to the same unannealed sample. Given the variety of experiments, I would say that there are more experiments showing that this is a loop current order than antiferromagnetism in the cuprates, although antiferromagnetism is not in doubt, and I don't think loop current order is in doubt either. So I pass now to the third part of my talk, which is to talk about the fluctuations of loop current order, and then quantitatively compare to, this is the attempt to get the omega over T scale. Okay, assuming that the symmetry in this region is loop current order symmetry, but you should bear in mind, as I have written here, that a translational invariant state, although with those peculiar symmetries, although that is detected there, cannot produce a pseudo gap in small Fermi surface. Okay, and this has been a thorn in my back for a long time, for which I may have a resolution now. I also wish to note here a very intriguing new paper which is in the archives by Dominic Elsa and Senthil Thodadri. And I'm very intrigued by this paper because I do not understand it very well. but it claims that they can prove that if you have a conductivity going as 1/T in the pure limit, which it does in these materials, that they can prove that that can only occur if it is at a critical point with the symmetry implied, or fluctuations of symmetry implied, which is a time reversal odd vector, which breaks inversion, therefore. So it's a polar vector, which is time reversal odd. And that is, of course, as they have kindly noted, the symmetry of the loop current ordered phase. So now I want to derive the fluctuations, or at least mention to you the solution. And let me tell you the kinds of things that went through my head in thinking about loop current order and its fluctuations. Now, let's take some good book on the old-fashioned way, but correct way, of doing quantum statistical mechanics, say the book by AGD. We know that there is an exact expression for the response function, any response function, which depends on this chi q omega, what response function is what vertices you put at the end. They're always related to putting exact single particle Green's functions and the exact vertex. This is a truism. And the self-energy can be related also to the exact vertex. The exact vertex, gamma, can in turn be written in terms of the irreducible vertex. And by irreducible vertex means that in the direction in which this diagram is shown, you have a repeated irreducible part. And after that, anything you draw the diagram can be split into two by just cutting a fully dressed particle and a fully dressed whole line. And inside I, anything can happen. Now, Landau theory, question, how do we break Landau theory? Now, this irreducible interaction concerns interaction at high energies. Landau theory assumes that I is completely regular, and the forward scattering limit of I is used to generate the Landau parameters. If I is regular, the only way at long wavelength, which is all that Landau theory speaks about, the only way to break Fermi liquid theory is through repeated particle hole scattering, this intermediate particle hole. And that gives to Pomeranchuk instabilities, and less rigorously at large Q. If you have charge density wave and spin density wave, then you have finite Q scattering, but the skeletal structure of the theory, given a regular irreducible vertex, is just generalized RPA. Now, an alternate way to break Fermi liquid theory is that there are singularities in the irreducible vertex. Somehow, that which in the non-interacting theory is at high energy has come down to zero energy. And as I said earlier, if that should happen not just in forward scattering, it's not just the singularity of Landau parameter, it should happen over over the entire momentum space. And this is a completely different ball game. And loop current order belongs to this category. And further, as I will show, its fluctuations are topological. And although we learn where to look, we should look in the irreducible vertex, deriving those topological fluctuations, conventional many-body theory is helpless. So let's do something else. And so now I'm going to speak about this quantum critical fluctuations, the model. And I already told you that the loop current order is really a vector order with 4 possible orientations. So if we were doing a classical theory, a theory for classical phase transitions on it, it would be a XY model with fourfold anisotropy, this parameter H4. Okay, and I'm allowed to put this extra 2 theta I minus theta j, although it doesn't do very much. Now, what we do know is that in the XY model, classical XY model, the fourfold anisotropy, it's incorrect here. In 2 dimension, for fourfold anisotropy, it's marginally relevant in the fluctuation regime, and it's highly relevant in the ordered regime. The ordered phase is described with the Ashentel. Now, the XY phase transition is not a phase transition that you can address, as you well know, by the Wilson, Fisher, Kadanoff way of doing statistical mechanics. It's a topological phase transition. And ordering occurs by binding of vortices of opposite circulation. Now, we have to do not the costless-Howlett transition, but the quantum version of that. And in the quantum version, besides these parameters theta, there is the conjugate variable, which is the angular momentum, the kinetic energy. And then what we can show very easily is that in the quantum model, the fourfold anisotropy is really irrelevant. Okay, we can show that analytically, but we can also show that by Monte Carlo. Now, it's very important when we come to quantum critical model to add in dissipation. And I'm going to add a particular kind of dissipation which can be derived in the model for completely different reasons. Tony Leggett and Caldera had suggested that kind of dissipation, and I'm going to describe that. Now, the phase transition is going to be driven by topological defects, what I call warps and vortices, and not by Wilson-Fisher kind unharmonic oscillations. And what is remarkable about this model is that you can solve this analytically just as well as solve the costless-Thouless model. So the analytical solution proceeds by finding an exact transformation from variables in terms of theta or grad theta, which is like a velocity, which I call in the rest of this talk M, to orthogonal topological excitations, not just vortices, but warps. But all these calculations have been supplemented by very detailed quantum Monte Carlo calculations on this model. Now, I mentioned vortices and warps. We all know what a vortex is. Well, in a, excuse me a moment. On a lattice, as shown on the left, if the velocity field on going around a 4 lattice sides, if there's a loop which is quantized to 2 pi, that's a vortex. It's a topological object. If you make a cut here, that phase difference has to be 2 pi across that cut. It's a topological object. What's a warp? That's shown on the right. And I've drawn 2 slices in imaginary time. And supposing there is a jump of the phase in M at a point ij without a jump at its neighbors of 2 pi, the jump of 2 pi and no jump on the neighbors, then you are creating a velocity field so that there is a divergence of the velocity field, which is allowed in the XY model only due to dissipation. And you end up in a divergence of the velocity field, which is shown on the right of this diagram. And that is finite now, at least at 5 points now, with a value 4 in the middle and -1 surrounded by it. So it creates a monopole of charge force surrounded by 4 monopoles of charge -1. That's very interesting because an object of this kind at sufficient distance away from it, having another object will have 0 interaction. That's going to be very important for the spatial independence or near independence of such fluctuation. You could try to solve this problem without introducing warps and vortices, and it doesn't work. The problem simplifies enormously if you introduce warps and vortices, and one can derive but do very detailed quantum Monte Carlo calculations, which were done by Lijun Zhu, and there are 2 long papers on it, and I'm going to show you just one result. Supposing you calculate the correlation function, this correlation function, e to the I theta, e to the minus I theta at different points in space and time. I call that g theta. And you calculate that, and I have plotted it here, tau times that correlation as a function of tau with respect to the parameters of the model, which are going to be tuning it towards the quantum critical point. And what you discover is that different parameters can be put in one scaled curve, and that scaled curve says that the correlation function is 1 over tau. The decay is not like e to the minus tau over psi of tau, the correlation length in space, but to the power half. I haven't been able to derive that half in analytically. I only get a simple exponent, doubtless due to deficiency in my learning of complex variables. And then there is a separately product form e to the minus x over c. How well this works, you can see that the tau sub c sub tau in the inset is plotted on an exponential scale on the vertical axis as a function of this parameter alpha away from critical, and you see that that scaling is indeed obeyed, and the c of tau is a correlation length. So this is the form that we are getting, and if you allow me to replace tau over c of tau to the power half in the exponent, whose Fourier transform I do not know how to do by simply e to the minus t over psi tau, and then let that c tau go to 0, and the spatial correlation length c tau go to infinity at the critical point, and the spatial correlation c sub x also go to infinity. This thing is simply 1 over tau. Now the Fourier transform of 1 over tau is tangent hyperbolic omega over 2t. So what I learned after 20 years is that it is not tangent hyperbolic omega over t, it is tangent hyperbolic omega over 2t. But we have now a theory, and the theory says some very remarkable and strange and unusual things. One is that the correlation function is a product function of space and time. Space and time have been liberated from each other. So there is a spatial correlation length to the problem with a simple Coulomb-like decay in space, but it is of a product form. And because the correlation function is a product of space and time, or of frequency and momentum, 2 things happen. It's very easy to calculate everything else. And secondly, it behaves very much as if spatially, the assumption that we made on spatial locality and derived the thing, it works for disseparable forms as well. Okay, and another thing we learn is what is called C here. Spatial length scale is log of the temporal length. That can be seen in Monte Carlo as well as analytically derived. Let's contrast this with conventional quantum critical spectra, which is shown on the top. So if you look at some correlation function, you know that far away enough from the phase transition, there's a big broad hump. I've drawn a function, the imaginary part, so it has to be odd in frequency and go to 0 at the origin. And then the weight gradually piles up towards lower frequencies as you go towards the critical point, and space and time are completely entangled. In the dissipative XY model, we have the behavior shown at the bottom. All that happens is that the fluctuation spectra gradually moves for omega small compared to temperature towards the origin, leading finally to a discontinuity in the limit of t going to 0. But the bulk of the spectra remains. There's always this cutoff omega sub c. It's a constant. So there's an enormously high density of states of these fluctuations over a large energy scale, and Q and omega are separable. Any questions on this?
Yeah, Chandra. What is the assumption that's made on the dissipation? What is the dissipation spectrum?
That's a very good question. I wish I could draw it, because I did. Maybe I drew it here. No. Okay. So so I'm looking at fluctuations of this variable theta phase. But phase cannot have fluctuation. Phase is not the right variable. Gradient of phase is a variable. So I'm going to be looking at gradient of phase, and gradient of phase is the current. It can decay into fermion currents. Okay, so I can draw a picture in which gradient of theta comes along, decays into particle-hole pair carrying current, and let's dress it as much as you like. I'm going to make an exact statement on it, and then goes off into grad theta. Now,
Yeah,
the current correlation is going as omega times the conductivity. And I'm going to take the limit of t going to 0 for that, and say that due to impurities or what have you, that's finite. Okay, so I'm going to get a mod omega from that, a constant which is related to the inverse t going to 0 resistivity, and then it's multiplied by grad theta square, which is q square times theta square. So it's going to be omega, mod omega q square theta of q omega square. That's the dissipation.
So you need some dissipation at 0 temperature. I mean, in the 0 temperature limit, right? So if the dissipation is coming from fermion.
I do need it. Yes, correct.
Okay, so let me understand again. So it's omega independent of q, just linear omega independent of q.
No. It's mod omega times q square times theta of q omega square. Okay?
Mod omega, I'm sorry.
Mod omega times q square times theta of q omega square. Okay? Now,
in Fermi liquid theory, it would have been omega divided by V of Q. Is that correct? If there's no disorder, it would have been omega divided by V of Q. Is that just to get myself oriented? That's the density correlation function, right? It's omega divided.
No, I'm doing the current correlation. Yeah, if it was just the density correlation function, then you'll get something else, but not omega over V of Q. Okay, because that has to be then.
Okay, yeah, that's one. So the dissipation is from the disorder.
Dissipation of that form is required. Although I should say that in doing quantum Monte Carlo, instead of theta q omega square and q square, we took cosine theta at 2 different places in space. Okay, and so in other words, we kept the model compact.
Yeah.
So if you keep the model compact, this kind of behavior does not happen. However, if you take that cosine theta square plus another term of this kind, even though the cosine theta square dissipation was an order of magnitude larger than the one omega q square, it is completely dominated by this non-compact dissipation. Okay, these are all in this quantum Monte Carlo. I could not do analytics with the cosine theta. Okay. Now, as I mentioned to you earlier, given this form of correlation function, it's very easy to calculate everything. Here I'm showing a skeleton diagram for the self-energy at the bottom. Now, what is this wiggly line? I'm going to take that wiggly line to be my fluctuation spectra that I've just derived. And that I mentioned is the irreducible vertex in the problem. Okay? Now we know an exact relationship between the self-energy and the irreducible vertex, which is shown on the top. And given that simple form of singularity in the particle hole channel in I, with a product form in Q and omega, this is very easily calculated. Okay? And you come to the fact that the imaginary part of the self-energy is going as linearly in omega, and therefore the real part is going as omega log omega. And these are non-perturbative calculations. And you can do other calculations. For example, you could calculate with these fluctuations the current correlation function to get your conductivity. And so the current correlation function, as shown at the bottom, is the exact single particle Green's functions put together with current vertices and a current vertex at the end. However, if the fluctuations are of the separable form or independent of momentum, you can show that lambda is 1. Okay? And you can calculate conductivity. You can calculate entropy. It's very easy. And now let me come to quantitative tests of the theory in the strange metal region. And I'm just not going to just talk about power laws, but I'm going to talk about coefficients. So as I said, if we calculate the self-energy, which was already obtained in marginal Fermi liquid theory, it goes as some coefficient times this pi over 2. This pi over 2 will be important because I want my accuracy to be better than replacing pi over 2 by 1. Then there is proportionality to omega plus omega. This, incidentally, this omega log omega will give me the marginal Fermi liquid, meaning that the quasi-particle renormalization goes to 0 as 1 over log. Now, these fluctuations have a natural cutoff, some high energy scale, which we'll get out from experiment, which is this omega sub c, beyond which the fluctuations are constant. Now, the first reliable experiments on the single particle scattering rates with angle resolved Fourier emission arrived by Kaminsky and Campuzano. It was Kaminsky's PhD thesis, and they looked at the Fermi surface along the cuts shown on the left, and you got these curves on the top. And those curves on the top are really, the red lines are really Lorentzians. Now in Lorentzians, it's very easy to read the width, but the fact that this line shape plotted as a function of momentum for a fixed energy is a Lorentzian immediately tells you that the self-energy is independent of momentum. Okay? Think about a moment and you'll see that that is true. And then fitting these lines, they fitted these lines to what I've shown on the right here in the small thing, where m sigma is plotted as a plus b omega. And so the line width is going as omega at the Fermi surface, is going as at q equal to k equal to qf along these cuts. And you see that this b is always lying between 0.6 and 0.8 within error bars. There's some other impurity scattering rate which is strongly angle dependent, but I'm not going to talk about that, although we fully well understand it due to forward scattering. But you see that this value of b is independent of momentum. It's independent as you go across the cuts. And this value is between 0.6 and 0.8. I called it 0.7 plus or minus 1, but my parameter G is really G pi over 2 is equal to B, so G is 2 over pi times B. So this G bar, this is coming out from experiment to be 0.4 plus or minus 0.1. So we know that the fluctuations are proportional to omega, the scattering rate is proportional to omega. It's essentially independent of momentum for the inelastic part, and its magnitude is given by this number. Let's go now to an experiment which was just done a year and a half ago, which is a measurement, very hard to do, by the group of Thierry Klein at Grenoble and Louis Taillefer's group at Sherbrooke, which is to measure the specific heat in LISCO with different dopings. And you notice on the left figure that there is something which we may call P sub C, at which the specific heat rises very strongly. And if you take the point closest to P sub C and plot it as a function of temperature, specific heat divided by temperature against log of temperature, it's a straight line to, they couldn't measure below 0.5 Kelvin and cannot measure, or phonons become important, about 10 Kelvin, but over that range, it is linear. So specific heat is C over T is indeed going as log, okay, which is the prediction of the theory. But the slope of the log should be related to the real part of the self-energy, which is related to the coefficient in the imaginary part of the self-energy. And from that, you can get out another value of G bar. Not only that, by extrapolating where this log term goes to 0, you can get the upper cutoff, Tx. G log Tx over T. You can read Tx from this. And what you find is G bar is 0.4 plus or minus 0.1, and Px is 1200 plus or minus 300. Okay, and Louis Taillefer talked about this. This is published result, but Louis also showed similar result in Bismuth 2201, also a log singularity in C over T. Let's go to the next experiment, because we got another parameter. We saw this parameter G bar is the same in the single particle scattering rate as it is in the specific heat. But we got another parameter, this omega sub C. For that, you have to measure angle resolved photo emission up to high energy. And this is all the data that exists in 4 different, one Bismuth 2201, one Bismuth 2212. I apologize to the experimentalists. They should have their name on the paper. The experiment by ZX Shen here, the experiments here by the guy in PSI in Switzerland, Johan Chang, and the experiments by Alexandra Lanzara here. And this is done to high energy, and you see that that it is essentially linear over most of the range, and then it becomes constant, just as you predict. And from this constant, you get out the cutoff. And you come to cutoff omega C, depending on what compound you're looking at, from 0.4 to 0.5 eV. And if you convert that to the temperature using Boltzmann constant and Planck's constant, you get 1300 to 1500 Kelvin, which is the same thing that you found within factor of 20% from the specific heat. Incidentally, I should say here that the maximum KFL that you come at 0.3, this is the momentum distribution curve, full width at half maximum. So it gives you the inelastic L. It's absolute value. If you know what the Fermi surface KF is, it comes out to be 0.3 at 1500 Kelvin. we need not worry about the off-illegal limit.
Chandra, just a question for clarification. What are these 4 curves and what are the green and cross ones?
Sorry, what are what?
What are these 4 curves? What are the difference?
There are 4 different compounds. There are 4 different compounds, 2 of them at slightly different angles, which is lanthanum, strontium, copper oxide at 2 different dopings. Okay.
And they are nodal or antinodal?
Sorry, these are all near optimal doping.
Yeah, but nodal or antinodal?
Sorry?
Nodal or antinodal?
This is in lanthanum, strontium, copper oxide. There are 2 different angles. Okay, nodal and another angle. And in bismuth 2201 and bismuth 2212, it is nodal. Let's go to the resistivity, the same compound that Thur showed the data of. And again, resistivity, as you know, is linear in temperature, and it varies. The slope varies from 0.25 plus or minus 1 to 0.4 plus or minus 1 measurement in different compounds. This is a factor of 3 lower than what they deduced. And this factor of 3 lower that I deduce is because I believe that when you calculate resistivity, I believe and I can show that when you calculate resistivity, the effective mass that enters is the band structure mass and not the renormalized mass. And I get this kind of number. People want to have these numbers close to 1 for some reason. I call it Planckian dissipation. But the other day I consulted Mr. Planck, and he said he likes 1 over pi better than 1. I had a seance. Now, if you look at the region in which the resistivity is linear in T, coming from the upper end, it is a mistake to try to fit, when you have criticality, resistivity by some of power laws. Power law expansion should not be done. You have to approach it from where it's critical, stop when it ceases, and then go from the bottom. You'll see T square, and stop when you don't see T square, and the region between the 2 curves would be the crossover curve. And this is what you find in lanthanum, strontium, copper oxide. It's only linear in between this region. Incidentally, this thing is x minus xc to the 0.5, this crossover curve, which is also how you can fit the rise here as x minus xc to the minus 0.5, which incidentally is a prediction of the theory. Let me go to something else, which is the density correlation function, which has been measured in Monte's group by Mitrano et al. A couple of years ago. It's a very hard experiment, but compared to calculating the conductivity, calculating the density correlation in the long wavelength limit is a hard job. Okay, it's technical. It's been done by Schechter and me about 8 years ago. And one thing is immediately obvious. If your conductivity goes as 1 over omega, the density correlation function at Q small compared to VFQ small compared to omega has to go as VF square Q square over omega square. Okay, that's just continuity equation, because the imaginary part of the density correlation function, as I've indicated in the equation on the left, has to go as the compressibility times Q square times the generalized diffusion constant as a function of frequency divided by frequency. Okay, and so you can fit this upper end. This has been done at a whole varieties of Q as a function of omega over VFQ by Monte, and extract a parameter G bar of about 0.6. Okay, and I would say that given the error bars here, it is not inconsistent with this 0.4 plus or minus 0.1. Incidentally, I'm not going to speak about that because I do not have quantitative comparison with other things, but this near constant to which these curves are going towards large omega is in fact even more interesting than this VF square, Q square, or omega square. And this is part of the prediction of the theory. And finally, there's this question of why 6 D-wave superconductivity and extraction of parameters from experiment. And I'm going to do that at the end, only if I have time, which doesn't look like it's going to happen, because I want to talk about the new thing, something which has, as I said, been a thorn in my back, which is how to understand properties here, which I hadn't been able to because I had loop current order, which wasn't changing translational symmetry. We know that this region has an anisotropic gap over most of the expected Fermi surface with a very small residual Fermi surface as deduced by very high quality magneto oscillation experiments by Suchitra Sebastian and Cyril, what's his name? Same name as the novelist, Cyril Proust, and I couldn't get that. And every time in the last 15 years that I would give a talk on the Cuprates, Patrick Lee would take great pleasure in asking me, but what about the Fermi arcs? Okay, so I have a tentative answer and a tentative experiment in relation to that. I would say Patrick Lee would torture me, but it was completely correct to torture me on that. So Fermi arcs are small Fermi surface oscillations. Okay, as I said, it cannot be obtained by the loop current order. But given that the loop current transition is the only symmetry which is observed at T star of any substantial magnitude, in half a dozen different symmetry-related experiments, and given that I can deduce everything in the strained metal phase quantitatively, better than we can do in almost any other metal. I had 2 parameters and I could fit 5 or 6 different properties quantitatively, not just the frequency dependencies, but the coefficients. It's been very hard to imagine for me that what is left in the experiment to explain is not related to loop current order. So I had to think of variations on it, decorations of it. So let's think of domains of loop current order. I mentioned to you that I have these 4 different directions. And you would think that in a macroscopic crystal, they would like to form domains. And the moment you think about it and try to organize domains, you find you can't arbitrarily do it. Because if you arbitrarily do the domains, there'll be currents flowing at the boundaries. This is not just true of this loop current phase that I'm talking about. This would be true of the Haldane phase or any other thing that you can make with the gauge symmetries, something happening in the inside of the crystal whose manifestations may or may not be there on the surface. So the current conservation, when you have boundaries, requires that they be organized in a specific topology. Okay, and if you think about it here, what you discover is that let me make 4 domains, each of 5 by 5 unit cells as shown here. Then I have to disturb all the boundaries. 8 of them are shown here in a specific fashion so that current is conserved. And you can do that with currents 0 or doubled at the boundaries, but you don't want to do that. Okay, that's very expensive. So this is the structure that I found which does that. I'm not sure whether it's unique, and there are lots of things about it which I do not understand. Part of the motivation of this was the Affleck-Su-Marston pi flux phase proposed already in 1988. Supposing you had flux as shown at the boundary happening across a square root of 2 structure, and it had pi flux. You know that the Fermi surface, the energy structure at half filling in a band with only nearest neighbor coupling changes to a massless Dirac spectrum. So I had expected that even in this situation, if I have domains of large enough size so that the total flux here is pi. Incidentally, the flux that I was talking about in loop current order is very small compared to pi, okay, 50th or so of pi. But that is not true. However, given this structure, I can actually, now it's a band structure problem. I can calculate, okay? Incidentally, let me say that this is topological in the following sense, that if I try to tile a whole system with the rules which are in this picture, which is that things which are oriented 180 degrees with respect to each other, everything here inside it, except at the near the boundary cell, has one particular orientation of loop current order. If I try to tile an entire space, I can do that by adiabatic deformation, and I can do it by the rule that oppositely directed loop current orders meet at points only in this fashion. This is a variant on the 4-color problem discovered by a postman in Yorkshire. Okay. So there's a certain stability about this. And you see that if you try to tile an entire space, and I have proved it by doing it on a large piece of paper with some 60 of these, and I know I can continue it. My proof is similar to how the postman proved the 4-color problem in Yorkshire in the early 1800s. And you'll see the structure. There is a vortex structure to the direction of these loop currents. And I have not fully yet understood all the implications of this, but I can calculate what should happen. Now, Patrick talked about this problem with somewhat similar motivation, of coming to a different conclusion, but it turns out it's not so unrelated. So I have now many mini Brillouin zones, okay? In that mini Brillouin zones, let me draw Fermi surfaces for each Brillouin zone. This thing in red, I call it a privileged Fermi surface because that was the original. And I have drawn here four other Fermi surfaces of 4 different mini Brillouin zones displaced from the privileged Fermi surface by, if P is the period, displaced by 1 over, if 2P is the period, by 1 over 2P, 1 over 2P, minus 1 over 2P, minus 1 over 2P, 1 over 2P, minus 1 over 2P, and minus 1 over 2P, and 1 over 2P. Okay, the 2 greens are the +1, -1, okay? And now you'll concentrate on the 2 greens and the red. Okay, so I call that a privileged Fermi surface, and the others, it's slaves, because in the absence of any translational symmetry breaking, and I'm going to deal with translational symmetry breaking, creating me supercells of size 2p by 2p. In the absence of coupling, you can draw these Fermi surfaces, but they have 0 spectral weight. You see, in the repeated zone schemes, I have the same energies, right? So I can do anything I like, but it's meaningless. That 0 spectral weight. It turns out, and it's very easy to see, that the weight acquired at other Fermi surfaces is of the order phi over p square. Displaced Fermi surface has weight phi over p square, where phi was the phase shift per unit cell, and p is the size of each domain. So they're tiny spectral weight. The other thing you notice is from the symmetry of the particular decoration that I did, that the couplings between the different Brillouin zones, Ks in different Brillouin zones, increases systematically from the nodal direction to the antinodal direction. And in the antinodal directions, you see that the Fermi surfaces are nearly parallel. And also, the region between the green curve and the red curve is hole for one of them and electron for the other. So I'm not going to do it by purely band structure. I'm going to do it as a instability. And then the region between the Fermi surfaces is an endangered zone because I have nearly parallel Fermi surfaces. I'm looking in the particle hole channel, unlike the particle-particle channel that Patrick was looking at, okay? And so the scattering is allowed, okay? Incidentally, look at this region, okay? This is gonna be important for me for magneto oscillations, okay? Because this is the region which is least affected. But at these points where the greens and the reds curves are crossing, they have identical energies and there is a finite matrix element. Okay, so when I calculate it by Mathematica, the Fermi surface, and Mathematica can give me intensities only, it seems to, within factor of 10, I get a Fermi arc. Okay, this is a straightforward calculation. If I blow up, so here were these three different Fermi arcs down in the bottom left. If I increase the intensities of the subsidiary regions by a factor of 10, the slaves by a factor of 10, you see that in that crossover region, now this is on a much more expanded scale on the x-axis and y-axis, and this is the Fermi surface. I find a closed Fermi surface. On the right, I show you the angular distribution at the Fermi surface as a function of angle for holes and for electrons. And for reasons that should be obvious, it is quite highly particle-hole symmetric. So I achieve the one of the amusing conditions for this pseudo gap and the Fermi arc. It's tied to the Fermi surface. Fermi arc remains in the center, and it's tied to the Fermi surface, but its particle-hole asymmetric. Okay. Now this is done by saying, you know, if you just divide up the Fermi surface, if you make a period 2 or a period 4, there should be other pieces visible. But if you divide it by 20, the intensity on the others is order, you know, 1 over 20 each, 1 over 400 each, and there are 400 of them. Okay, and you'll never see that in ours. Okay, but this central region may be what is seen in magneto oscillations. Now, what I have said, like almost everything else I have said, is subject to a diffraction experiment. Okay, and I proposed that diffraction experiment, and there were some preliminary results. And if the national labs had not closed due to COVID, this would have been done, but it hasn't been done yet. And therefore, I am not sure that this idea is the final idea. However, as I said, there's a new experiment, and the new experiment is photogalvanic effect in bismuth 2201 and bismuth 2212 by Sijun Lim, working with Aaron Kapitalnik, that I have helped analyze. So this is a very detailed experiment in which you come in with photons and you measure DC current. It looks like the converse of second harmonic generation, like second harmonic generation, but it's actually technically quite different, and even analytically it is quite different. So you can do two things. You can measure, come in with circular polarization and measure the current shown in the first line, and that depends upon a matrix gamma L, which has to be an axial second order matrix. Or you can come in with linearly polarized light and measure current in the sample in different directions, and that is a third rank polar tensor that is required. And in Bismuth 2201 and in Bismuth 2212, you observe, I think this is in Bismuth 2201, you observe below 2201, after you have subtracted out a surface contribution, a non-trivial contribution shown in red, both in circular polarization and in linear polarization, shown in the two parts of the curve. So there is some symmetry breaking, and now you have to analyze the data. Now, what is remarkable about this effect, as opposed to neutron scattering and the way the second harmonic generation is done and analyzed, is that you're observing an effect over few tenths of a millimeter of the sample, and the effect observed is linear in the order parameter. How could you possibly observe something which is linear in the order parameter, which is going to be oriented all over the place? That's one question. Second is that by varying the angle and the polarization, both azimuthal angle and the other angle, the polar angle, you can make 11 different observations. And then given the 11 different observations, you can go to your table of point groups and ask yourself, what are the groups which satisfy all different 11 criteria? And it turns out there are only two groups, 2 point groups, MM2 and a closely related group, MM21 prime. And neither of them are the symmetry that neutron scattering observed, which was something called M bar MM. Okay, the symmetry that is observed is lower. Also, you're observing chirality. You see, with this CPG, the circular polarized galvanic effect. So there are only two possibilities. There's no time reversal breaking. Then the structural domains, and then you have to ask that at T star there are the structural transformation in which the crystallites, tiny crystallites, become monoclinic and they organize themselves in a chiral fashion. And then you can make a macroscopic symmetry of the MM2 kind, of the kind observed. With time reversal breaking, if you organize loop current order in domains, which I suggested a year and a half ago, again, you get MM2 symmetry, and you can show that in detail, it would be consistent with polarized neutron scattering done to its present resolution, the Kerr effect, simple harmonic, second harmonic generation, and dichroic harvest. That is this symmetry that I exhibited for you. This symmetry is MM2. Okay, I think I have probably gone already over time. Yeah, I have. So I'm not going to speak about the last issue, which is how to get D-wave superconductivity from my fluctuations, and simply end and ask for questions. So I've talked of this phase diagram, and I would say that the strange metal properties are as well understood in the cuprates as any metal that you know. I've not been able to talk about the symmetry and transition temperature of superconductivity and analysis of Xingzhang Zhao's experiment. I proposed this periodic modification of loop current order to understand Fermi surface, Fermi arcs, and the small magneto oscillation. There's a very preliminary, there's an experiment which is consistent with it, but I never come to conclusions on the basis of one experiment, I need at least 3. But if a diffraction experiment comes along, then I will say that we understand the cuprates. So I thank you very much for patient hearing, and apologies for going 10 minutes over time, and I will wait for any questions that you may have. Thank you.
Thanks, Chandra, for a nice talk. Yeah, any questions?
Thank you very much.
Chandra, very nice talk. My question is, what does your theory say about the spin charge stripes that appear, about the pair density wave evidence seen in, I think it's LSCO, but I have to go look. In other words, there seem to me to be other orders that your very rich theory doesn't address that are seen in the cuprates, and particularly the spin charge stripes.
Okay, so Doug, in some ways, I answered that question right in the beginning in this slide when I said, keep in mind the relative thermodynamic importance of different transitions. And supposing I look at the charge density wave order, which is seen along this dashed line in yttrium, barium, copper oxide, which is the best established charge density wave order in any cuprates. And the best established is measured in a magnetic field above 20 Tesla. You can, from the intensity of the subsidiary Bragg peak that they generate, estimate the thermodynamic significance of that. And you find that the characteristic energy of that is of about 1/10 of a degree per unit cell, okay? And of superconductivity is about 10 degrees per unit cell, okay? So I regard these as insignificant things which happen differently in different compounds, and therefore, at first brush, not worth thinking about too much. And I believe the same is true of essentially the other things that you talked about, and I believe that they are thermodynamically even less important than the largest charge density we've seen in yttrium, barium, copper oxide. I'm interested in properties which are universal in the cuprates, and the things that I've talked about shown in this phase diagram are the only ones that I know that are universal and substantial.
I would only comment in rather extensive numerical calculations on Hubbard and TJ models that the stripe and the competition between stripe, charge density, and pair field stand out much more than any evidence for circulating currents.
Okay, my reply to that is, Doug, that for investigation of things like stripes and whatnot, Hubbard model is even more inappropriate than the usual copper oxide model that I've talked about. I can go to it in great length about why there is some indication of stripes in compounds having to do with the solid state chemistry of the copper oxide. You see, if you go from copper oxide to nickel oxide, you find nothing but stripes. Okay, and there's a reason for that. Okay, and that's an issue which I can talk about at length, and I had thought about that 25 years ago, but I don't want to go about it now. Okay, you can always pick your model and calculate anything you please. Okay, I'm interested in properties which are universal. Okay, the properties in the strained metal phase are universal. The properties in the loop current order phase that I talked about, the symmetry breaking and the Fermi arcs are universal. The D-wave superconductivity is universal. The fact that antiferromagnetic fluctuation occurs quite apart from this region, the fact that the antiferromagnetic correlation length in the region of the maximum superconductivity
can I ask the next question?
That is constant, is important. There are some important problems, as I said, about the antiferromagnetic.
So I'd like to take you back to the gap formation. So as I understand it, the gap is coming from the. Can you hear me? Oops.
Yeah, go ahead.
Yeah. So as I understand it, the gap is coming from breaking of translational symmetry in the X and Y direction. So that's similar to a density wave type gap. And as I think I mentioned last time, the trouble with that scheme is that you can easily get Fermi arcs, but if you look at the spectrum, the way the gap closes is from the state coming from above, not below. In other words, ARPAS would be able to see the gap. So I wonder if you have actually done the spectral calculation to verify that.
Patrick, I'm very aware of that, and I would say that that is the issue that you alluded to in ARPAS is answered here from the lack of particle hole symmetry in the solution here, and it has to do with the fact that by making an enormously large number of periods, I have to deal with scattering between states around this red Fermi surface and the states around the green Fermi surface. And I believe that question is answered.
Okay, well, I would like to see the details, but yeah. By the way, I should point out that that objection only refers to translation breaking along X or Y. If you have pi-pi scattering, then you could have states coming from.
Of course, there is pi-pi scattering here as well.
Yeah, so pi-pi scattering could help you there. But,
if there are anybody still listening, if there are any questions, you can ask me now, but you can also email me. I'll be happy to. I'll be delighted if you email me, and I'll write you as thorough an answer as I can.
I have a question.
Hello?
Hello? Hello?
Sorry.
Yes. Can I ask a question?
Yeah, go ahead.
Oh, yeah. So I wanted to ask about this dissipation. If you have dissipation, it means you must be coupling to a bath, right? So what is the bath for you?
The bath is the fermions themselves.
I see,
and the way I calculate the properties of the fermion, like for example, I calculate the conductivity of the fermions, right? I get a vertex. I use the same vertex for the dissipate, and when I scatter off the fluctuations, I need some coupling, right? Some coupling function to calculate self-energy and to calculate conductivity. I use the same vertex as I must for calculating the fluctuation propagator or the fluctuation Lagrangian, okay, by coupling it to the fermion currents. Okay, because only the current in the fluctuations, grad of theta, something which transforms as current of the fluctuations, couples to the fermions, okay? So I use the same vertex. So if you go to, there is a progress in theoretical physics 2 years ago, this question of dissipation and what vertex is used is discussed there, okay? So you might want to look it up. Incidentally, I would still love to talk to you and Senthil about your paper sometime. As I say, I'm very intrigued by it and I have many questions on it.
I'm confused by your answer, Chandra, because when you answered my question, you said that disorder is important for this fermion. The dissipation really comes from the disorder.
In the following sense, okay, which is not okay. So this vertex here, can you see my view graph?
Yeah, yeah. Mm-hmm.
Okay, so here was my fluctuation propagator, right? And here's my some skeleton diagram. So this vertex has some momentum dependence, okay? So I'm using the same object and I am coupling up as I'm coming down from this fluctuation propagator. Think of the diagram for the self-energy of the fluctuation propagator. It will couple to these dressed particle hole lines and end up at the other fluctuation propagator. And that dressed particle hole line will be carrying current. And let's say it's carrying the exact vertex, it's the exact current. Okay. Now, that is proportional to omega sigma omega. Okay. Now, I have to take the t equal to 0, omega going to 0 limit of that.
Yeah.
Okay. So the leading thing that I can do two things. You see, because it is omega sigma of omega, I can either put sigma of omega going as 1 over omega and get a constant, okay, with a coefficient, or I can put out the DC resistivity in the limit of t going to 0. Okay, and I believe it is the second one, okay, because that's how I calculate.
Yeah.
Okay, that's my answer. In either case, it is omega q squared times sigma of omega, and I have to take the leading omega dependence of that.
Yeah.
The leading omega dependence of that is given by omega times sigma of omega if sigma of omega is finite at omega going to 0.
Yeah, so disorder is crucial. So have you studied the how it depends on the size of this sigma naught? How your answer depends on your answer must depend on the size of this sigma naught.
I can give you one answer to that.
Yeah.
So let's put a coefficient alpha in front of that. Okay, alpha over 4 pi. Okay, and this alpha is normalized to whatever h over 4e square. Okay, so when that coefficient the critical that there are two directions in which we can move to get criticality. We can either change the ratio of the coefficient in front of the angular momentum of the fluctuations, or the Josephson ratio of that to Josephson coupling. That's one way of traveling. The other way of traveling is to travel with alpha. Okay, I believe the former is more important. Okay, because that's what gives me this exponent half for the crossover. Okay, from linear resistivity to the other thing. So that's where alpha minus alpha c comes in. However, I don't have to be near alpha c. Okay, I can vary the ratio of the Josephson coupling to the kinetic energy parameter to tune my transition. Does that address your question?
We may be getting into too much of a detail. Maybe we should do this offline.
I know.
Without writing and so on, it's a little hard for me to follow.
Yeah, you know, this dissipation, this necessity of dissipation, and what all dissipation works and what does not work, is an important problem, which needs to be addressed in detail. I agree with that.
Yeah, because you started out saying that you want to treat the zero temperature limit without disorder, but I think at the end of the day,
I need some finite dissipation.
Yeah, that's right.
In the limit of t going to 0 to retain that part omega. Okay?
And I think that would go outside of the Cento-Elsa theorem. Once you have disorder, then they have nothing to say.
Yeah, I think there are issues there. If you find the rest of the story reasonable, perhaps you'll think of it.
But sorry, just a conceptual point. So the evolution of a full system, all the degrees of freedom, fermions plus the XY field, etc., it should be unitary, right? I mean, or do you agree with that?
Sorry, it should be what?
Should be unitary evolution, the full system.
This is a question in relation to dissipation, that if there is any loss of energy, it is not unitary. That's what your point is?
Yeah, Dominic, I think once you have disorder and you do disorder averaging, then it's not unitary.
Oh, with disorder averaging, yeah, okay.
Yeah, I think that's.
I mean, but you can consider one.
I think that's a very good point, because I need some dissipation. I need a sink. I need this divergence of the velocity field. Okay, and I for example, in the ordinary XY model, you do not have that. Okay, I have that here. I need dissipation, and maybe that's what Dr. Elsa means, that makes the model non-unitary.
Yes.
However, again, this is an issue which I wish I understood better. If you look at how the analytic solution of the problem proceeds, as opposed to the Monte Carlo solution where we put in omega q square, etc., right? That's what you put, that's what goes into Monte Carlo. But when we do the analytic solution, that omega q square business, the total dissipation, is absorbed by the definition of the warp. Okay, that warp becomes the time derivative of the divergence of the velocity field. Okay, and that becomes a well-defined excitation. You can lose phase in jumps of plus or minus 2 pi. Okay, in time, in imaginary time. So the moment we go to the analytic equivalence of the model to vortices and warps, the problem looks unitary. Okay, and that may be in some sense related to some kind of averaging that Patrick is talking about, but not impurity averaging in the conventional sense. Okay, this is an interesting theoretical issue, which I wish I understood better.
Yeah, thank you.
Anything else?
Any other questions?
Mm-hmm.
So if not, let's thank Professor Chandra again for a very nice talk.
Thank you.
Thank you.
Thank you.
Thank you, Subir.
Thank you.
Thank you, Doug.
Good to see you. Have a good day.
Hope to see you when things get better in life.
I feel the same way.
Okay, bye-bye.
Bye.
All right.
Thank you, Chandra.